let's look at power. Last section for this one. Power is the rate at which work is done or energy is expended. So it's the rate at which we transfer energy, basically. Power is work divided by time. Power is easy. It's measured in watts. Work is work done. And delta T is time taken. Sometimes you're going to have to calculate the amount of work done. Sometimes you won't. You just need to look at the equation. So, for example, the engine of a 300 kilogram dragster exerts an average forward force of 53,000 newtons over the first 20 meters of its race. A dragster takes 0.8 seconds to cover those first 20 meters. It goes very fast. That's the point of a dragster, okay? The whole point of drag racing is to go very short distance in the quickest time. First thing they want is to know how much work is done by the engine. Well, we're going to use F delta X cos theta. The engine is exerting 53,000 newtons of force onto the car itself, the dragster. The delta X, it goes 20 meters, and of course theta is in the same direction, so it's 0 degrees. So it does 1,060,000 joules of work going 20 meters. That's incredible amounts of work. Now they want how much power is developed. Well, power is work divided by time. They told you it did this in 0.8 seconds, so it's 1,060,000 joules of work that was done, divided by the time it took, okay, which means it's 1,325,000 watts. That's a very, very powerful engine. We would usually refer to this in kilowatts when it comes to cars, so this would be 1,325 kilowatts. Kilowatts we divide by 1,000. But for us, we work in watts. That's the SI unit. Another example, a power lifter is able to lift a large weight through a vertical height of 1.5 meters in 3 seconds. The weightlifter applies an average upward force of 2,700 newtons. They want the power output. All right, so we want power. Power is work divided by time. I need to know how much work is done. Well, the work done would be F delta X cos theta, and there really should be, so I'm just going to add it in here, a delta over here. That's a typo. Okay, so there's a delta over there. We know the force, 2,700 newtons. We know the height, 1.5 meters. We know the time. The force is being exerted in the same direction as the height, so theta is 0. So it's 2,700 times 1.5 times 1, because cos 0 is 1, divided by 3, 1,350 newtons. Watts. It's small compared to the car, but that's expected because it's a much smaller force over a much smaller distance. Okay, so it makes it easier. Make sure you do activity 2 because those are nice simple power questions. However, power is not always as simple as that. When a force is applied to keep a body moving at constant velocity, it balances the resultant of all the other forces. So what that means is if F net is 0. If F net is 0, then the net work done on an object also becomes 0. This poses a problem for us if we're going to be using F net to work out power. However, if we look at the applied force on an object, okay, so now we're looking at a specific force on an object, it would be F delta X cos theta delta T, but V, velocity, is delta X over delta T, you know that, so I can replace delta X over delta T with V, and the force would be in the same direction as motion, so theta is 0. Cos theta, or cos 0, is 1. That changes my equation to being average power, so this would be the average power of the applied force of the on the object, is that force times velocity. This is only valid when the object is moving at constant velocity. If velocity is changing, in other words, there is a network being done, you cannot use this equation. Right. So, on a straight level road, a cyclist with a power output of 95 watts can cycle at a maximum constant speed of 5. Calculate the force. Well, we know P average. Now here, if you put a V or V average, it doesn't actually matter. 95 would then be equal to F times 5, 19 newtons. Fairly straightforward. A vehicle of mass 2,000 kilograms travels up a plane inclined at 25 degrees to the horizontal. Oh, now we've got an incline. At a constant speed of 8 meters per second, the vehicle experiences a frictional force of 1,500 newtons. Draw a fully labeled force diagram showing all the horizontal forces acting parallel. So this parallel word there is very important to the inclined plane. Parallel, force of the engine moving it up, gravity pulling it down, force of friction pulling down. Straightforward. Now they want the force exerted by the vehicle's engine. You know that F net is 0 because it's going at constant speed. FG parallel you can work out, and you were given friction. So, that's FG parallel. FG, 2,000 times 9,8. We minus it because in the opposite direction, so it's going to be sine 25 minus 1,500. So they're helping us here. We know that the force of the engine is 9,783,32 newtons. It's a weird little number, but we're okay with that. We now know the force exerted by the vehicle's engine. Because we know the force exerted by the vehicle's engine, it means that we can work out the power of the vehicle. Watch. Now they want the power. Well, I know what velocity it's going at. It was going at 8. I know what the force was that the vehicle was expending. So 78,266,56 watts. Very, very straightforward. It's really not as difficult. However, in our curriculum, the minimum power to pump a water from a borehole, they love these because now we're moving things up. Okay? So what we have to realize is the upward force exerted by a water pump or a pump of any sort is a non-conservative force. Okay? Does not conserve mechanical energy. So for example, an electric motor drives a water pump which is submerged at the bottom of a borehole that is 8 meters deep. Calculate the minimum power of the electric motor required to pump water at a rate of 21 liters per minute. Per minute. We've got a rate here. Okay? So, first of all, 1 liter of water is 1 kilogram. So 21 liters is 21 kilograms. It goes 8 meters. It does it in 1 minute, which is 60 seconds. Okay? Velocity is constant. What I need to do the power is I need to know the force. The force applied is going to be Fg. It's going to be the weight of the object. So the work done by the non-conservative force, delta Ek plus delta Ep, delta Ek is 0. It's going at constant velocity. Gets to 8 meters, we need to minus the initial. So my force is having to do 1,646,4 joules of energy. Power is work divided by time. We know that's 27,44 watts. From here, I could work out how fast it was going if I really wanted to, because I could use P equals V times F times V. Now, to finish off this section, you need to the activity on page 182, and you're going to look at questions 2, 4, and 6.